Good morning, everyone. Today we're looking at Unit 2, Lesson 10, Review. So the front page of this note I already filled in for you to copy down. I didn't think you needed to sit while I wrote it all out, but I will talk through each of the vocabulary that should be in your mind and you should have a good understanding of for your Unit 2 test. So the first thing, the main point of this unit was polynomial functions. So remember, a polynomial function is an expression in the form y equals axn, ax to the power of n, dot, 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 right? And there's going to be more terms added or subtracted to that. The important part to remember about this is that n must be greater than 1 and a whole number. Okay, no negatives, no decimals in our exponents. Some examples of polynomial functions: we could have a linear function, y equals mx plus b, or a quadratic, y equals ax squared plus bx plus c. So that's our polynomial functions. Some of the key features we talked about with polynomial functions: a degree of the function, the leading coefficient. Is the function an even function or an odd function? Which, remember, talked about having to do with symmetry, not to be confused with an even or odd degree of a function. And also the multiplicity of a function, domain and range of a function. And then we looked at local maximum and local minimums. So the degree of a function is just the highest exponent on your independent variable. So on your x variable, what is the highest exponent on x? If you look at the example there, the 3 is the highest exponent, so it has a degree of 3. When we're looking at our leading coefficient, that's the a value in your function. So that number at the front of your function that's attached to your highest degree variable. So f of x equals 4x to the power of 3 plus 2x. 4 would be our leading coefficient. And in this case, it's a positive 4. So that positive 4 tells us something about our n behaviors. The next thing we looked at were even functions and odd functions. And like I said, that had to do with the symmetry of those functions. So a function which has line symmetry in the y-axis, remember, it can be reflected over the y-axis. So the example we had was something like this, right? Where you could reflect it over the y-axis, it would be exactly the same. And if we wanted to show that algebraically, we would substitute in a negative x for x, and the result would be the original function f of x. An odd function is a function which has point symmetry. So when we were looking at those functions, we were more looking at cubics, that if we rotated half of the graph 180 degrees, it would sit directly on the other half of that graph. And if we wanted to represent that algebraically, we would plug in a negative x for x, and the result would be each term in the function would have turned negative. So we would say f of negative x is equal to negative f of x. The next thing we looked at was multiplicity, which discusses how many times a zero appears in a function and then tells you what happens at that zero. So in our example, f of x equals x plus 1 to the power of 2 times x minus 3 to the power of 1. We can see that their multiplicities will affect what they do with the x-axis. So our negative 1, 0 will have a multiplicity of 2, which means it just kisses the x-axis, it just touches it. Our 0 of 3 has a multiplicity of 1, which means it does in fact cross the x-axis at that 0. Domain and range, nothing new. Domain is your x values of a function, usually represented as x for all real numbers. Our range is the y values of a function, so we want to look for absolute maximums or minimums to be part of that range. Because if we have an absolute maximum, then our range should be nothing above that. So it would be y less than or equal to that. If we had an absolute minimum, then our y value would have to be equal to that or higher, because that's the lowest point on the graph. So we could have y for all real numbers such that y is greater than or equal to negative 2. So in that case, negative 2 would be a minimum, and all other y values would be higher than that. A local maximum, local minimum, those just represent a highest or lowest point for a section of the graph. And you can see that in the little depictions next to the definition. Okay, so let's look at some graphs and talk about all these key characteristics we've looked at in this unit. All right, so we have a graph here. Let's see if we can identify some of these key features. So we have a cubic, so our domain is going to be x for all real numbers, right? That graph is going to extend on in both directions, so we're going to eventually get all of our x values. So we'd say x for all real numbers. In our range, you can see our graph continues on to the left, going more and more negative, and continues on in the right, getting more and more positive. So we will eventually also hit all of our y values, so y for all real numbers. Local maximum, we have a local maximum in this section of the graph right here. I'm going to say local max. And we have a local minimum in this section of the graph. It looks like around -6. Pay attention to the scale, because you can see that our scale here is 5, 10, 15, 20. So that local max is probably going to happen around, I'd say, 26. And our local min, again, the scale we're going down by -5. So I'd say we have a local minimum probably around a -6. Okay, and then we talked about sketching polynomial functions if we are given an equation in factored form. So if we look at this equation, we could start by identifying what type of function we have here. So we have x to the power of 1, and it's being multiplied by x to the power of 2, which means we're going to have x to the power of 3. So we have a cubic, or a degree of 3. The sign on our leading coefficient, so remember our leading coefficient is right here. We have a -1, so we can say we have a negative leading coefficient. What are our zeros? We can see it, pull our zeros right of our factors here. So we have a 0 at -2 and a 0 at +3. And if we look at what's happening on those zeros, right, the multiplicity, right, that one has a multiplicity of 1, so it's going to cross at that 0. But our other 0 has a multiplicity of 2, which means it's just going to kiss the x-axis or just touch it at that point. So our actions at zeros, for -2, it's going to cross. And for +3, it's going to just touch the x-axis. All right, and one other point we could figure out is our y-intercept, which just helps our graph look a little more accurate. So if we substituted in a 0 into our function, I have 2 times a -3 squared is going to be a +9. So f of 0 is going to be a -18. So let's sketch our zeros first. So we have a 0 at -2 and a 0 at +3. We know if we have a negative cubic function, then that's going to be similar to a negative line where it's up to the left and down to the right. So at our zeros, we can mirror those end behaviors. We know we're going to be up to the left and we're going to be down to the right. All right, we also know our y-intercept. So let's let each of our y intervals go by -2. So say -2, 4, 6, 8, 10. So this is -10. And we'll say this one's -20 down here. So then I can plot my y-intercept at -18. So from my 0 at -2, I know I'm going to cross the x-axis because it has a multiplicity of 1. And we're going to come down here to my y-intercept. Try to make that curve a bit more smooth. All right, and then from there, we're going to go back up to my next 0, which is at +3. Remember, my +3 is just going to touch the x-axis. It's not going to cross because of the multiplicity of 2, and then come back down right on the end behavior. All right, so there you go. We were able to sketch that from the key features we identified in the factored form of the equation. All right, last thing we did in this unit, we talked about finding the equation of a polynomial function. So first thing we're going to do is we're going to determine the zeros. So we have a 0 here, here, and here. So those zeros are at -3, -1, and a +1. So we're going to work backwards. We're going to put those into factors. We have x + 3, x + 1, and x - 1. All right, so those are our factors. If we want to write the general equation we're going to have f of x equals a. Remember that a represents some kind of stretch or compression. And then finally, we have to put a point into that equation to figure out what a is going to be. So let's choose a point that falls right on the grid line, which I think this is a good point here. It's our y-intercept. So we have a point at 0, 2. So we're going to substitute that point in. Into our general equation. So substitute 2 in for our y. We don't know our a yet. And we're going to sub in a 0 for our x. So I have 0 plus 3, 0 plus 1, 0 minus 1. Okay, we multiply those together. 3 times 1 times negative 1 is a negative 3. And finally, we'll divide both sides by negative 3. So we'll have a negative 2/3 equals a. So then we can write our equation. We can say f of x is equal to a negative 2/3, and then all of those factors of x plus 3, x plus 1, and x minus 1. And that's it for your review.